Are you able to see my screen? PPT screen?
Yes, sir.
And my audio is clear, na?
Yes, sir.
So this is where we are ended. You can say at the last point of our class, not ended. Last point of our class. So this slide gives the briefly whatever topics we have covered till now. So till now, what was our main aim was to conclude or to understand how heat transfer is similar to momentum transfer is similar to mass transfer. So there what we got. So initially we have started the discussion with molecular flux. Okay. So molecular flux. Then we got three equation. So this is Newton's law of viscosity, which is correlating momentum flux with viscosity and velocity gradient. And then we have, so this is heat flux. Heat flux equals to thermal conductivity into temperature gradient. Then we have a mass flux, which is equals to mass diffusivity multiplied by concentration gradient. Then we have discussed this heat diffusivity also and momentum diffusivity also, and got some dimensionless number. But these are the two basic laws, you can say: Newton's law of viscosity, Fourier law of heat conduction, and Fick's law of diffusion. Then convective flux, it's very simple, because convective flux velocity is a characteristic of convective flux. Velocity, wherever there will be velocity, there will be convective flux. So velocity, this velocity will be inherent part. This is we are discussing in y direction only. So assuming that other fluxes are negligible, only in y direction. This is y direction, this is y direction. So this is y direction. So if velocity is there, so quantity per unit volume, x momentum flowing in y direction by convection. This, what is it representing? This is x momentum. Rho into Vx is a momentum per unit volume multiplied by velocity. That will give you x momentum flowing in y direction because of convection. This is also x momentum flowing in y direction because of molecular conduction. This is conduction, this is convection. Similarly, heat transfer, this is a temperature or flux in y direction, heat flux in y direction. Heat flux in y direction because of convection. Convection is giving me heat flux in y direction. This is conduction in y direction. This is conduction in y direction. This is mass flux in y direction because of convection. Cy into Vy. So this is the mass flux in y direction because of convection. Okay, this is convective term. This is convective term, and this is the mass flux in y direction in molar form because of conduction. So this is what we have discussed initially. So then we observed that at the interface, when we have complex nature of flow characteristic at interface, because of presence of two different phases will give me complex nature of flow characteristic at interface. So this equation is not able to give me total flux, as total flux will be convection plus conduction. Convection plus conduction. Then we got three new equation. This is Feining equation, which will give me interface flux in you can say momentum transfer, interface flux in total interface flux. So which is relating viscosity, which is not relating viscosity, friction factor. So friction factor is related with the velocity, and we got this Feining equation, which is giving me molecular momentum flux at the interface. Similarly, this is also total flux at the interface, and this is Newton's law of cooling. This is Newton's law of cooling, and this is again, you can say, Slattery equation or Newton's law of mass transfer, which is relating interface mass flux, total interface mass flux. So now these are the, you can say, equations which we have discussed in last 10 classes. And overall, if you go in basic subject, basic heat transfer, basic mass transfer, and basic momentum fluid mechanics, so these are the equation which is controlling the designing parameter almost 99% basic. Then what in advance you will get? You will get a complex how to handle the complex flow characteristic, that you will understand. There sometime transient, how to handle the transient problem, that you will understand. So these are only addition part, but basic will remain same. So then you need to handle partial differential equation in advanced subject and all. So but these, I will say, almost 99%, 90% of total subjects, heat transfer, mass transfer and momentum transfer, will be somehow governed by this equation only, this equation only. So now, so if we observe closely this equation, so what is most important in this equation is, if I want have viscosity and friction factor, so almost you can solve 90% of the design problem in fluid mechanics. Okay, so viscosity, friction factor, and here velocity. So how velocity is varying. Okay, here also velocity. If I have three factor, this viscosity, friction factor, and variation of velocity. So viscosity, friction factor, and velocity profile. If I have these three parameters, so I can solve almost 90% of the design problem in fluid mechanics. Velocity profile, getting velocity profile is not easy. So that is what these three. Similarly, in heat transfer, if I have how to estimate the thermal conductivity, how to estimate the heat transfer coefficient, and how to get the temperature profile. If I know this, I can solve almost all problems in heat transfer. All design problem can be solved. Similarly, in mass transfer, if you know how to get the diffusivity, how to get the mass transfer coefficient, and how to get the concentration profile. So if I know this, okay, so almost 90% of the mass transfer is solved. So as I can say, the abstract of whatever topics we have discussed. So if I know viscosity, thermal conductivity, and diffusivity estimation, similarly friction factor, heat transfer, and mass transfer estimation, similarly how to get velocity profile, how to get temperature profile, and how to get concentration profile, I can solve all the problem in heat transfer, mass transfer, and momentum transfer. 99% of the problem in transport phenomena can be solved. Only the thing is, if you are transient problem, this is for steady state, I'm saying. Transient state, transient, this viscosity behavior will be different. So whatever this partial variation, transient and unsteady problem, so that will be added in advanced subject. Okay, that will be added in advanced subject. So fundamental transport phenomena will study this only: estimation of viscosity, thermal conductivity, and diffusivity, and secondly, estimation of friction factor, heat transfer coefficient, and mass transfer coefficient. Third one will be how to get a velocity profile, temperature profile, and concentration profile. Now remaining almost, I told 30 to 35 classes will be devoted for this only, out of which almost 80% is for how to get the profile equation for velocity, temperature, and concentration. So this briefly we will have. So there is a theory associated with how to get viscosity, thermal. So briefly we will discuss this. So maybe 10% of our efforts will go for this estimation of viscosity, thermal conductivity, and diffusivity. 10% of effort will go for this friction factor, heat transfer coefficient, and mass transfer coefficient. Now remaining whatever classes, 80% of the classes will be for getting this velocity profile, temperature profile, and concentration profile. So this is what you can say. Our base is ready now. Base is ready for transport phenomena, on which we can build our information. So what we are going to build is how to get the viscosity, thermal conductivity, and diffusivity, and how to get friction factor, heat transfer coefficient, mass transfer coefficient, and most of the knowledge, whatever we are going to discuss, whatever the information we are going to discuss, will be how to get the velocity profile and temperature profile and concentration profile. So this is what we are going to do hereafter in transport phenomena. So now today we will be discussing analogy available in transport phenomena. So till now what we were saying that this Newton's law of viscosity is similar to Fick's law of diffusion, is similar to Fourier law of heat conduction. It is similar. Okay, this equation is similar to this equation is similar to this equation. Similarly, here also in interface flux we got this equation. Okay, this is Feining equation is similar to Newton's law of cooling is similar to Slattery equation. This is what we are similar. You might have heard hundreds of times, but nowhere we have seen that. So thermal conductivity equals to viscosity, or temperature equals to velocity, or concentration equals to velocity equals to. It is not so equals to is different and similar is different. So what are the transport analogies? They will equate the area. They will equate. So if say huge information in heat transfer, but you want to calculate some information in momentum transfer. So using the property in heat transfer, you can get the property in momentum transfer accordingly. So that is what a analogy is there. So analogy will equate the area, heat transfer, momentum transfer, and mass transfer. There are thousands of analogy available in literature. Thousands, I am telling, not one or two, because these are all experimental observation. So people will observe heat transfer experimentally, and people will observe momentum transfer experimentally, and then they will try to correlate heat transfer with momentum transfer, mass transfer with momentum transfer, and so on. So these all, there will be some limitation for each and every analogy. That is what we are going to discuss now. So transport analogy from current slide. Okay, so this is pointer. Can you see the transport analogy screen on your screen?
Yes, sir.
Yes.
Okay. So what are transport analogy? Till now we were saying that Newton's law of viscosity is similar to Fourier law of heat conduction, is similar to Fick's law of diffusion. Similarly, that Feining equation is similar to Newton's law of cooling, is similar to Slattery equation. Similar. But with some limitation, these are equal also. So if flux in heat transfer I want to estimate, with the limitation from where this limitation is coming. So whatever scientist has given an analogy and his observation limitation, the experimental limits with which he has observed this similarity or equality. So if say viscosity is given, so if you want to calculate the heat transfer coefficient, or viscosity is given and you want to calculate the thermal conductivity, this can be done. Similarly, friction factor is given. Friction factor is given and you want to estimate the heat transfer, rate of heat transfer. So there are some analogies which you can use. So given a friction factor, you can get the heat transfer coefficient. Given a calculated heat transfer coefficient, you can get a rate of heat transfer. These are all analogies. So we are, as I told, there are thousands of analogies available in literature. Thousands. So almost every year you will find 10-15 publication on analogy, this transport analogy. So but this was initially started by Reynolds. Initially, so first analogy was proposed by Reynolds, and some added information, some added observation was given by Chilton and Colburn. So these analogies are widely used, you can say in book and all. But according to new observation, new techniques are coming. So you can go in fine observation and all. You can observe all this property on minute micro levels also. So new analogies you can come across. Okay. So but we are not going to cover all the analogies. Same. So we are going to cover only Reynolds analogy and Chilton-Colburn analogy. So these are the two analogies we are going to cover, and how these analogies are discussed, how these analogies are established. That base we are going to discuss in this class. Okay. So already we have discussed. Okay, what is this equation? This is the equation which we got during a physical interpretation of friction factor. So if you remember this equation, half friction factor into Reynolds number will be equals to characteristic length divided by delta. So this characteristic length will be the dimension which is the property of my system. Okay, characteristic length. So this characteristic length will be a diameter in pipe. If I am discussing flow through pipe, this characteristic length is diameter. Flow over flat plate, it will be the length length in a direction of flow. Length of the plate in a direction of flow. This is how people are doing. Okay, most of the observations are based on diameter. So if I'm telling Reynolds number for flow through pipe, certainly you will not be taking length of the pipe, you will be taking a diameter of the pipe. Okay, dv rho by mu. So this is Muggup equation. So everybody knows this, Reynolds number equals to dv rho by mu. So nobody will tell me that okay, Reynolds number for flow through pipe is length of the pipe, length rho mu by d length v rho by mu. Okay, length of the pipe nobody will take, because this is standard people are using. Characteristic length for flow through pipe is the diameter of the pipe. Similarly, for flow over flat plate, it will be the length of the plate in a direction of flow. There people will not use width for Reynolds number, defining Reynolds number and all. So wherever, so this characteristic length is the dimension which is the property of our system, whatever system we are using, and which is commonly used. So it doesn't mean that okay, so you cannot use length in Reynolds number for flow through pipe. You can use. Then whatever this thing, you cannot say that okay, if Reynolds number is less than 2100, it is laminar flow. If Reynolds number is greater than 2100, it is turbulent flow and all. Because you have altogether changed the definition of characteristic length. Instead of using diameter, you can use length of the pipe. Altogether observation will be different. So this is why generally we will adopt the general nomenclature, general what people are using in literature and all. So if you change that, you can change. It is not wrong that you can change. But whatever observation, what people have reported and all, you should not compare them. Okay, you should not compare where Reynolds number D diameter is used, Reynolds number less than 2100, laminar flow. You may get some other Reynolds number then using length of the pipe. Okay. So likewise, this is characteristic length, and this is what half friction factor into Reynolds number equal to characteristic length divided by delta, where delta is a momentum transfer boundary layer thickness. This already we have discussed. So you can see this is the discussion. So this is the discussion. So this is first observation we got. Okay, this is first observation we got, where we got the physical interpretation of friction factor with respect to a viscosity and rearranging the equation. And this is what we got finally, half friction factor into Reynolds number. Here also you can say LCH V infinity rho by mu, LCH. So this is diameter for pipe. This is diameter for pipe. So easy to understand. So this half friction factor into Reynolds number will be equals to LCH divided by delta, where delta is a momentum transfer boundary layer thickness. So this already we have seen. So rearranging this equation. So characteristic length. So diameter in pipe, or whatever be the characteristic length of the system will be equals to half friction factor Reynolds number into delta, where delta is a momentum transfer boundary layer thickness. Okay. Similarly, when we go to heat transfer, so this is what we got, physical interpretation of heat transfer coefficient. Physical interpretation of heat transfer coefficient will be equal to thermal conductivity divided by heat transfer boundary layer thickness. Okay. So this is, you can say, the heat transfer boundary layer assumed in ideal case. So and this is the physical interpretation where we got heat transfer will be equals to K by delta T. So just recall this. So these are all equations we have combined and got the physical interpretation of heat transfer coefficient. Similarly, we got the Nusselt number equals to HL by K. This is the ratio of two fluxes. What are these two fluxes? This also you can recall. Interface flux divided by molecular. This already we have covered in a class. So you need to go back and discuss this, revise this. Okay, interface flux divided by molecular flux. Rearranging, we got transfer coefficient characteristic length divided by diffusivity. So Nusselt number HL by K. So this already we have discussed how it is representing interface flux divided by molecular flux. So this is the physical interpretation of heat transfer coefficient and the ratio of interface flux divided by molecular flux. Now combining these two equations, you can see here also I have K, here also I have K. So here also I have H, here also I have H. So H by K is 1 upon delta. Okay, H by K is 1 upon delta. You can substitute it here and rearrange the equation. Rearrange the equation. So LCH will be equals to Nusselt number into delta T. Okay, and rearranging the equation. So LCH, you rearrange these two equations and H by K equals to 1 upon delta, or delta T will be equals to K by H. So delta T will be equals to K by H. So I'm rearranging the equation. So characteristic length will be equals to Nusselt number into delta T, and delta T is a heat transfer boundary layer thickness. So this is from heat transfer, observation from heat transfer. Similarly from mass transfer, so this is what the equation we got while discussing a physical interpretation of mass transfer coefficient. So mass transfer coefficient is a ratio of DAB. So ratio of DAB, and you can see this is ratio of DAB divided by mass transfer boundary layer thickness. And then what is the equivalent discussion? As we are discussing Nusselt number, what will be equivalent dimensionless number in mass transfer? Roll number 8, Ali.
Sir, Sherwood number, I think.
Sherwood number. Very good. What is the physical interpretation of Sherwood number?
Sir, Sherwood number equal to.
Yeah,
I
what
think
is physical interpretation? Physical, how we have interpreted
Sir.
that physically?
Yeah,
Physical
sir,
meaning of
convective.
Sherwood number?
Yes, sir. Convective, sir.
Yeah,
Mass
that
flux.
is, yeah.
So conduct.
Yeah, it is not convective divided by conduction. It is total interface flux divided by total conduction. Okay, but most of the time this total flux, interface flux, will be referred as a convective flux. Why, Ali?
Because, sir.
So you can see this is Sherwood number. Okay, this is physical interpretation of mass transfer coefficient and Sherwood number. This is also called as the Nusselt number for mass transfer, and this is the ratio of interface flux divided by molecular flux. And now, as Ali told me that this is not a ratio of interface flux divided by molecular flux. This is the ratio of convective flux divided by molecular flux. Whether this is wrong or right, Ali? You are telling it is the ratio of convective flux divided by molecular flux. I am telling it is the ratio of interface flux divided by molecular flux. So which is correct, which is wrong?
Sir, actually, I am not remembering correct definition.
Hey, don't give me this S-cube, man. Not remembering. And I have given a simple assignment 1, 2, 3 for you. Okay, and some people have posted also whether they can submit whatever notes they have written in a class itself. Okay, you are not expected to, that is not your notes, that will be a short notes, just you have written for understanding the subject. What will be actual notes? Actual notes will be a, for 1 hour of the class you need to spend 2 hours in reading. So for every 1 hour of the class, you need to spend 2 hours in reading. That is 1 credit course. Okay, 1 credit course. Okay. So for 4 hour of the 4 credit course, so I am taking 4 hours, and you need to spend 8 hours every week in reading from reference book, other information available for same topic, and then write your notes. That is actually your notes. Okay, and then after 10 class you keep on telling me that you don't remember. So it means that you are not going to get anything in this subject. You are not going to get anything in this subject, and it will be in turn waste of your time. So you will get grade, you may get grade AA also, but for understanding the subject and for using this subject in future, it will be zero. Nothing you are going to get in this subject. It will be waste of your time, waste of my time, and most importantly, it will be waste of your father's money. You are wasting that. Okay, and just giving me excuse that you don't know. That excuse you can give anything, but in turn what you are doing is you are wasting your time, you are wasting my time, and most importantly, so hard earn money of your parents you are wasting actually. Just telling me that you don't know. Yeah, roll number 21.
Yes, sir.
So whether interface flux divided by molecular flux equals to Sherwood number is correct, or whether convective flux divided by molecular flux equals to Sherwood number is correct.
Interface, sir, which is like displaying on screen. Interface flux by molecular flux is like Sherwood number, sir.
So
Cause it is
convective flux divided by molecular flux is not correct, Sherwood number or Nusselt number. It is wrong.
conductive also. No, sir. It's conductive also. It's correct, sir. But
Yeah, very good, very good. Both are correct. Why? Why?
sir, when conductive is dominating,
Yeah. Most of the time, whenever there is a convection, it will be dominating.
yes, sir.
So convection can be, you can say, represent as a total flux itself. Okay. Whenever there is a convection, molecular flux will be negligible. Okay. Whenever there is a convection, molecular flux will be negligible. So sometimes this interface flux is referred as a convective flux.
Yes, sir.
Sometimes it is referred as a interface flux. Sometimes it is total interface flux. Sometimes it is referred as a. Both are correct. I'm not telling that is wrong. Okay, but both are correct, because whenever there is a convection, 99% of the flux quantity will be governed by convection, and only you can say minute. There will be minute quantity will be. You can say minute flux will be there due to molecular flux. Okay, so this is why. So this is, you can say, this is physical interpretation of mass transfer coefficient, and this is the you can say ratio of interface flux divided by molecular flux, which will give you Sherwood number. Again, here you can say delta C will be equals to Kc divided by DAB. So Kc divided by DAB will be a delta C. Okay, not delta C will be equals to DAB divided by Kc. So DAB divided by Kc will be equals to delta C. And rearranging the equation, what I will get? I will get characteristic length will be equals to Sherwood number into delta C. This is momentum transfer boundary layer thickness. So this is all this momentum transfer. No, this is not momentum. This is mass transfer boundary layer thickness. This momentum transfer boundary layer thickness. This is heat transfer boundary layer thickness, and this is mass transfer boundary layer thickness. These are the thought quantity. These are not actually present quantity, that using some equipment you can measure this boundary layer thickness. These are the thought parameters introduced in a discussion. Okay, what is this? Delta momentum transfer boundary layer thickness, heat transfer boundary layer thickness, and mass transfer boundary layer thickness. These are the thought parameter introduced in a discussion, so that you can give some model form to a physical observation. So whatever physical observation is there, so to put in equation form, these are the thought parameter introduced. So as such, there is no mass transfer boundary layer thickness. Okay, as such, there is no mass transfer boundary layer thickness, but there is a something. There is a something which can be assumed, using which you have given that as a name, mass transfer boundary layer thickness. Now whole of the your observation can put in a model equation, and then once you got a model equation, it will be easier for you to discussion, design, and everything will be easier. So that is most important. Okay, so these are all thought parameter introduced in a discussion. So likewise, there will be many parameters. So while going in kinetics, mass transfer, heat transfer, thermodynamics, and all, thermodynamics, many times you will have some such kind of thought parameters introduced for simplifying the discussion, so that a equation form can be given to a experimental observation. Okay, so now you can see, so this is also LCH. Okay, characteristic length from momentum transfer boundary layer thickness. This is also characteristic length from momentum transfer boundary layer thickness. This is also characteristic length from this is from heat transfer boundary layer theory. Okay, this is from mass transfer observation. Okay, this is momentum transfer, this is mass heat transfer, and this is mass transfer. So everything is characteristic length. As I told, this characteristic length will be diameter. If we are discussing flow through pipe, so flow through pipe diameter will be equals to half friction factor Reynolds number into momentum transfer boundary layer thickness. So similarly in heat transfer, flow through pipe, heat transfer you are discussing, so diameter will be equals to Nusselt number into heat transfer boundary layer thickness. And this is mass transfer, diameter will be equals to Sherwood number into momentum transfer boundary layer thickness. So these are all characteristic. So LHS equals to same. So LHS equals to same. So now here I can equate. Okay. So this will be equals to this, will be equals to this. Okay. This will be equals to this, combining 1, 2, 3. So I can now equate, because everything, this is characteristic length of a system, which will be equals to half friction factor Reynolds number into delta momentum transfer boundary layer thickness. That will be equals to Nusselt number into delta T, and this will be equals to Sherwood number into delta C. This is say 4A. So this is the first generalized based on which all analogies will be developed, from which all analogies will be developed. This is first generalized. So this is also characteristic length. This is also characteristic length. This is also characteristic length. Now all analogies will start with this equation only, or so now I can rearrange this equation. I can rearrange this equation, put some other definition of Reynolds number into in terms of Nusselt number and Sherwood number, like you can say rearranging. So this is Nusselt number divided by Reynolds number, rearranging. Okay. Now this equals to this equals to this. So half friction factor into delta will be equals to Nusselt number divided by Reynolds number into delta T will be equals to Sherwood number divided by Reynolds number into delta C. So this is not equals to LCH, but as these three equations are same, LCH, so I can rearrange, divide all three by Reynolds number, divide all three by Reynolds number. So Nusselt number divided by Reynolds number and Sherwood number divided by Reynolds number. Okay, this is second generalized analogy equation. Sometimes you will find people will start with this equation. Sometimes you will find that people will start with this equation, or there is another definition which already we have covered. Ratio of Nusselt number divided by Reynolds number is a product of Stanton number for heat transfer. Okay, Nusselt number divided by Reynolds number will be equal to Stanton number for heat transfer into Prandtl number. You go back maybe I think 3-4 classes before this. At one point we have discussed this, how Nusselt number equals to Stanton number Prandtl number divided by Reynolds number, or Nusselt number divided by Reynolds number equals to Stanton number into Prandtl number. Similarly, Sherwood number divided by Reynolds number equals to Stanton number for mass transfer into Schmidt number. So substituting this here, so combining this equation, so what I can get is, I can get half friction factor into delta will be equals to Stanton number for heat transfer into Prandtl number into heat transfer boundary layer thickness. That will be equals to Stanton number for mass transfer, Schmidt number mass transfer boundary layer thickness. So this is first equation 4A. So what all these three equations are called as a generalized form of transport analogy. These will be the base for derivation of the any analogy. As I told, there are thousands of analogy present in the literature, but you will find somehow it will be either starting point will be this equation 4A or 4B or 4C. So somewhere you will find that every analogy will start with this observation only, where it will start with a basic this characteristic dimensions. So people will derive this and then they will go for analogy, or they can take directly. Maybe they can refer some equations, some literature, and directly they will use as f by 2 delta and Stanton number for heat transfer, Prandtl number, delta T and delta. Now here only the thing is how this delta T and delta C is behaving. How, what is their observation? That is what people are putting in for different cases, because these are all thought parameters. They will observe, they will certainly behave differently for different system. So how it is behaving? They will try to correlate this with measurable parameters, and they will put in this equation and get the analogy. So these are called, this equation 4a, 4b, and 4c are called as the generalized transport analogy. So everywhere you will find that these analogies will start with this equation only, and then they will put the, now we are going to discuss Reynolds analogy and Chiltern-Colburn analogy. There also you will find same thing. There also you will find that, okay, it will start with this equation only, 4c, both the analogies. Okay, so anybody has any confusion over this generalized transport analogy? Okay, then we'll discuss Reynolds analogy. As I told, all analogies will start with any one of the generalized transport analogy. Okay, so I got the generalized transport analogy 1 upon F into momentum transfer boundary layer thickness will be equals to Stanton number for heat transfer into Prandtl number delta T. That will be equals to Stanton number for mass transfer into Schmidt number into delta C. So, and this, what is Reynolds observation? So Reynolds has observed for some limited cases. What is that limited cases? When you can using a gases, okay, gases related heat transfer, gas related mass transfer, gas related momentum transfer. He observed that momentum transfer boundary layer thickness equals to heat transfer boundary layer thickness equals to mass transfer boundary layer thickness. So this limitation, this assumption, okay, this assumption or whatever be the experimental limitation of a researcher, that will go as a limitation of that analogy. So what is the limitation of Reynolds analogy is it cannot be applied for liquids, flow of liquids. It cannot be applied for liquid because he has observed for gases. And moreover for gases, okay, so what I will get if delta equals to delta T equals to delta C. So what I can get F by 2 equals to Stanton number for heat transfer into Prandtl number. That will be equals to Stanton number for mass transfer into Schmidt number. And already we have seen what is the order of magnitude of Prandtl number and Schmidt number for gases. Here roll number 20, Aviral. Aviral, what is the order of magnitude of Prandtl number and Schmidt number for gases?
So Schmidt number and Prandtl number.
Yeah, Schmidt number and Prandtl number. Order of magnitude.
Sir, the Schmidt will be.
Yeah, Aviral.
Yes, sir.
Yeah, just tell me truthfully actually, how much time you have spent for transport phenomena other than class timing till now? Other
Sir,
than class timing, you have spent a 0 hours.
no, sir. Sir, for some parts of notes to complete, sir, I have used it.
Okay.
That really, sir.
So you want like this some like animals, people will pin the thing, na? Until and unless I will pin you, you will not start walking. Okay. So just
No, sir.
asking you that, okay, do this thing is not enough. So I need to have that pin. So I will use the pin and then you will start walking. Okay, you should. So what is the order of magnitude? Roll number 44, Narendra. Roll number 44, Narendra.
Yes, sir. Yes, sir.
Yeah, what is the order of
Sir,
magnitude?
for gas, sir, Prandtl number for gases it will be 1, sir. For liquids it will be 10, sir.
Okay, and
For
Schmidt
Schmidt
number?
for gas it will be 1, and for liquids it will be 10^3, sir.
Yeah, exactly. That is what Reynolds also used. So this is true. This is assumption 1. Assumption 1, or you can say observation 1 or limitation 1. So limitation is coming from whatever experiment Reynolds has conducted. Reynolds has conducted all the experiment for gases only. So what he observed, delta equals to delta T equals to delta C. And how he has concluded that, if you want to go in details, so you can go in the research paper of Reynolds, where he has given an analogy first time. So you will find almost 15-20 pages paper and discussing everything, how he has concluded delta equals to delta T equals to delta C. Okay, here just we are taking what is his conclusion, what is his observation. So, and secondly, Prandtl number, Schmidt number equals to 1, and this is true only for gases. This is only true for gases. So if I incorporate this, Prandtl number equals to 1, Schmidt number equals to 1. So what analogy I will get is F by 2 equals to Stanton number for heat transfer equals to Stanton number for mass transfer. This is called as a Reynolds analogy. This is Reynolds analogy, where say you can say Stanton number for heat transfer, you have heat transfer coefficient. Stanton number for mass transfer coefficient, Stanton number for mass transfer, you have mass transfer coefficient. If the friction factor is given, I can estimate heat transfer coefficient. And estimating heat transfer coefficient, I can do the calculation in heat transfer. Similarly, if friction factor is given, I can get the mass transfer coefficient and I can do the calculation in mass transfer. Similarly, say mass transfer coefficient is given, I can do the calculation in momentum transfer. But this is true only for gases. This is known as a Reynolds analogy, and all the properties. So there are some other properties also estimated. So these are estimated at average temperature, average operating temperature. Same wall temperature might be some different, bulk temperature might be some different. So all properties are estimated at average temperature, and this is valid only for gases. Okay, so just knowing analogy is not important. Okay, so now you know Reynolds analogy. It doesn't mean that so whatever calculation you are expert in heat transfer, now you can do whatever you want in momentum transfer also. Is it doesn't mean just knowing analogy is not important. With analogy you should know its limitation also, and that limitation will come from whatever the limitation of experimentation that researcher have done, based on which observation he has given that analogy. So here Reynolds has worked with a, you can say, gases only, mass transfer in gases, heat transfer in gases, and momentum transfer for gases and all, and put his observation and all the properties he has estimated at average temperature. These two are the most important limitations, most important limitation of Reynolds analogy. So all the properties are estimated at average temperature, and this Reynolds analogy is valid for gases only. So this is Reynolds analogy. So this is clear to everybody. So knowing analogy is not important. So you should know the limitations of that analogy also. Otherwise, you keep on going this using this Reynolds analogy equation everywhere, because this analogy is so easy. F by 2 equals to Stanton number for heat transfer equals to Stanton number for mass transfer. Now I can use anywhere. Okay, so that will be wrong actually. That you will get wrong answers as such. Okay. Then secondly, Chilton-Colburn analogy. So Chilton-Colburn analogy. So again same thing. So Chilton-Colburn analogy will also start with same equation. So as I told, so this is 4C equation. 4C, as we have discussed in couple of slides back. So any analogy will start with this fundamental equation. Fundamental 4A equation. You can see this is what I was referring to. Either it will start with this equation, or it will start with this equation, or it will start with this equation. These three equations are called as the generalized transport equation. So this is also Reynolds analogy is also derived from this 4C equation. And now I can have Chilton-Colburn analogy. Okay, what is observation of Chilton-Colburn? Okay, so Chilton-Colburn has observed within its limitation. So delta by delta T equals to Prandtl number raised to 1 by 3. Okay, delta by delta T equals to Prandtl number raised to 1 by 3, and delta by delta C. Okay, so momentum transfer divided by heat transfer bond layer thickness equals to Prandtl number raised to 1 by 3. and momentum transfer divided by mass transfer boundary layer thickness, that will be equals to Schmidt number raised to 1 by 3. This is the observation of Chilton-Colburn analogy. Observation, or you can call it as an assumption, or you can call it as a limitation. Okay, delta by delta t equals to Prandtl number raised to 1 by 3. And substituting this, friction factor divided by 2, that will be equals to Stanton number for heat transfer, Prandtl number raised to 2 by 3, that is equals to JH. This is called as the heat transfer J factor. This is called as the heat transfer J factor. It is commonly represented as small jh. Okay. Similarly, F by 2 equals to Stanton number for mass transfer, Schmidt number raised to 2 by 3. So rearrange the equation. Put delta by delta t equals to Prandtl number 1 by 3, and this Prandtl number 1 plus 2 by 3. 1 by 3 will be equals to 2 by 3. So F by 2 equals to Stanton number for heat transfer, Prandtl number is to 2 by 3, that is JH factor, and this is JM factor. So what is the limitation of this Chilton-Colburn analogy? So this is JH and JM factor. This is called as a Colburn J factor. Okay, Chilton-Colburn J factor for mass transfer and heat transfer. So limitation. This observation he has observed with all the property estimated at average temperature. Secondly, Prandtl number should be between 0.6 to 60. Okay, 0.6 to 60. So this analogy holds good for gases also, and this analogy is good for liquids also. Okay, liquids also it is good. Similarly, Schmidt number between 0.6 to 3000. So you can see this Chilton-Colburn analogy is widely used analogy. So which is commonly used because this is true for gases also, this is true for liquids also. Now certainly if you use for gases, say Prandtl number equals to 1, if you use Reynolds analogy, it will give different answer. If you use Chilton-Colburn analogy for gases, both are true for gases, so it will give different answer. So there can be variation in answer also. That variation can be plus minus 20-25%. Why? Because these are all kind of semi-engineering correlation. Engineering correlation means you have your observation is put together to estimate these theoretically defined quantities. Theoretically defined quantity observation. And so some equation you want to quit, so certainly there will be error. So this is the limitations of Chilton-Colburn analogy. In addition to this, so here you can see flow over flat plate. Okay, flow over flat plate, F by 2 equals to JH equals to GM. Flow over flat plate. Okay. So this is Chilton-Colburn analogy. F by 2 equals to JH, F by 2 equals to GM. Stanton number for heat transfer into Prandtl number raised to 2 by 3. So, and these are the limitation, and these are the geometric limitation. For flow over flat plate, F by 2 equals to JH equals to JM. For flow over cylinder, it is not F by 2 equals to JH equals to JM. It will be only JH equals to JM. Flow over sphere. So flow over sphere, JH equals to JM for Nusselt number greater than 2. In Sherwood number greater than 2. These are all limitation. There is no theoretical background why these are all limitation. This is coming from whatever experiment done by Chilton-Colburn, that they have done the experiment for Nusselt number only up to 2, and they have put their observation. Similarly, flow through pipe, F by 2 equals to JH equals to JN if Reynolds number is greater than 10,000. If the Reynolds number is greater than 10,000, then this is true. F by 2 equals to JH equals to JM. Otherwise, JH equals to JM. JH will be equals to JM. That is true for all the cases. All the cases. So why this? Sometime there is F by 2 is coming, sometime F by 2 is not coming. Here F by 2 is not coming, here F by 2 is not coming. Because of this, for flow or flat plate, so this F by 2 is nothing but the shear stress. Shear stress that is pressure per unit area. So this is pressure or shear stress or force per unit area. So now here when there is a flow or flat plate or flow through pipe, this surface area for heat transfer is equals to surface area for mass transfer is equals to surface area for momentum transfer. But on curved surface like this, in momentum transfer, you will be taking a projected surface area for calculating shear stress. So exactly same thing is done while you are designing, say, tall vertical vessels. For tall vertical vessels, shear stress, for calculating shear stress, you are just use the area length of the this distillation column divided multiplied by diameter. You are not taken a surface area. Why? Because for calculating shear stress, you will be taking a projected surface area. So from here, what is the projected surface area? So this length multiplied by width will be the surface area for momentum transfer. But for heat transfer, this is the surface area for heat transfer. Whole will be the surface area for heat transfer, and for mass transfer also this will be the surface area. That is why, so surface area for heat transfer will be equals to surface area for mass transfer always. Hence, JH will be equals to JM always. But sometimes surface area for momentum transfer is not equals to surface area for heat transfer. Hence, F by 2 will not be equals to JH equals to JM. Okay, F by 2 will be equals to JH, F by 2 equals to JM, and you will have different this thing actually. So when F by 2 will be equals to JH equals to JM, when surface area for heat transfer equals to surface area for mass transfer, that will be equals to momentum transfer. So these all limitations is clear to everybody. Any confusion over here? Any confusion over here? Okay, then we'll continue our discussion in tomorrow's class. Thank you very much for attending this class.
Excuse me, sir.
Yeah, tell me.
Sir, there was one doubt.
Tell me.
So while going through the physical interpretation of our phenomena, the three phenomena,
Okay.
while obtaining the expression, we were used to add the convective and conductive flux and then go through by neglecting the convective term,
Yeah,
right, sir?
yeah.
But that was at y equals to 0.
Yeah.
And now the generalized definition is like whenever there is convective and conductive phenomena, the convective is always dominant. It
Yeah.
always dominates.
Yeah.
So, sir, the y equals to 0 thing is factoring here, like in expression. We are neglecting the convective term, but we say that if there is convection, then it will be dominant. It will be
Yeah.
dominating.
Yes.
So, sir, like if like that's the doubt, sir. Like why we are neglecting convective while writing the expression, and we are saying that convective is only
No.
dominant.
Look, we are discussing interface flux. Interface flux means from wall, what is the heat transfer to the liquid from the
Okay.
wall. So first layer is coming into picture. So what is the
Yes.
velocity at first layer? It is 0.
Right. Okay, sir. Yes. Of course.
So
Yes.
certainly, so I'm not adding heat from somewhere else. Whether I am adding heat in second layer directly, no.
No.
When in first layer there is no velocity, so how convective term will be there?
Yes, sir. So if in whole system the convective is dominating, but while
Yeah.
we are seeing
In,
the no slip
so as
boundary
soon as
conditions,
I move in bulk, I forget about interface flux and I move in bulk. Now molecules are moving and there is a flux because of moment of molecules also. There is a flux because of this gradient of driving force also. That time there I can discuss convective and molecular.
okay, sir. Thank you, sir.